It's a pretty common situation. People get their first e-bike, it works awesome, they're super happy, and then something breaks down. 2 to 3 years after they bought it, the item's no longer manufactured or supported, the bike shop that they got it from isn't around, or they don't really have any clue how to diagnose and troubleshoot electronics, and people are left with a very expensive piece of scrap metal, often winding up in the landfill for no other reason than some small component that's failed that nobody knows how to identify and fix. So here at Grin, we hear about this all the time, but our business is entirely about conversion kits. We're really not there to service and fix factory e-bikes, but we do understand in principle how you can generally resurrect almost any electric bicycle and make it work again. So in this video series, we're going to review that process on a RadRunner e-bike, which is about the easiest platform for doing these kind of conversions on. We're not here to promote this. If you have a working e-bike, you really shouldn't touch it unless you know what you're getting into, and you have to take full ownership that by delving in and hacking things, you may break things and make it stop working, and that's nobody's responsibility but your own. But if your bike is already broken or out of commission, and there's nobody around who knows how to fix it, but we're going to show you some of the nitty-gritty details that are involved in repowering an e-bike with third-party components. We're going to go over an example case using this RadRunner fat tire bike and do a controller upgrade to Grin's Frankenrunner motor controller that will allow us to then increase the power and speed of the vehicle, and it will also allow us to upgrade from a basic cadence sensor into a torque sensor. Now, the Rad bike that I've got in front of me is an example of a pretty ideal platform for doing this. Not all factory e-bikes are as easy to work on. What makes the Rad systems, at least those offered to date, quite amenable is that they've kept their components fairly generic and fairly non-integrated. The Rad batteries are separately mounted down tube batteries, just like you get on many conversion kits. The Rad motor controllers are actually mounted as an exposed discrete motor controller. Now, on most factory bikes, the motor controller is going to be hidden inside the battery pack, somewhere inside the framing, and in the worst cases, the motor controller will be inside the motor itself. In that case, you're much more limited in your ability to swap out the motor controller for a different controller. And finally, Rad has been quite consistent about using a connector plug between their motors and the motor controllers, the Z916 connector, which we have an adapter for all of our motor controller series. So this particular bike, because the battery is mounted externally, if the owner of this bike simply wanted more range, it'd be a very straightforward job to replace this 48-volt 13-amp-hour battery pack with one that had higher capacity. There's down tube batteries that will fit in that same space, stick out a little bit further, and get you upwards of 20 amp-hours. So in this particular example, what I'm going to be doing is replacing the motor controller with Grin's Frankenrunner motor controller. And this is something that you do if the e-bike had completely failed electronics that you weren't able to diagnose, but you were able to confirm that the battery was fine. And it's also something you would do if you wanted to get potentially more power or speed out of the motor, or if you wanted to add interesting control features that you can do with our version 3 cycle analyst display. So here, the stock controller has just a very basic up-down button level indicator. It doesn't actually have a dashboard showing speed, volts, watts, or any of that useful information. So the switch to the Frankenrunner controller will give us a much more comprehensive display. But more importantly, the Frankenrunner, as a field-oriented controller, is able to run this motor even beyond the normal top speed and lets us individually tune the phase currents and battery currents to potentially get more continuous and short duration power out of the hub. Now, before we dive right into that, what I want to do is initially establish just the baseline performance of this bike with the stock motor controller so that we can compare what actually happens when we switch out to the higher power Frankenrunner controller. So to do that, we're just going to install the standalone cycle analyst using all the existing electronics that are here, and that'll just let us monitor and see what's going on in the power with the system as it came. So the Rad bike is using a overmolded 2-pin plug between the battery and the motor controller. So what we need to do is tap into this wire to measure how much power is flowing. So we're just going to snip the cable and install a pair of Anderson connectors, and that'll let us plug our cycle analyst shunt in line with the existing battery leads and measure how much power is flowing through. That's going on the controller side. Plug things in and slide the battery in. And turn this on. Ideally, we'll see power. Sure enough. So the cycle analyst powers up. Now, in order to get the details that we want, we need to set the bike to have the correct wheel circumference. So we measured these to be just a tad over 22 inches. And that 22 inches is the same as a circumference of 1765 And we'll just need to run a speedometer sensor down on the front wheel. Now that we've got the standalone cycle analyst installed, we can ride around the block a few times and establish what the baseline performance is like with the stock RadPower controller setup, and that'll give us a great reference for how it compares once we upgrade to the PhaseRunner or Frankenrunner motor controller. So we're just going to do a full throttle run, look at the acceleration, what the power is like as the speed accelerates, and find out what speed the power drops off. And here we go. So off the line, we're seeing just a tad over 500 watts, accelerating up to 20 kilometers an hour. 5. Great. Okay, so now we see the power dropping down to like 200 watts once we hit 30 kilometers an hour. I'll need a steeper downhill section to see at what point it drops to 0 watts, so we could just lift the wheel off the ground. So it looks like the stock controller is set up to be pretty much by the book, abiding by the Canadian e-bike regulations. So it never drew more than 500 watts of power or 510 watts of power over the entire speed range. And then the power immediately started to roll off once you hit over 30 kilometers an hour and was on its way to drop down to 0 watts once you hit 32 kilometers an hour. So that's not unexpected. Now the regulations related to power are rather confusingly written, and at the very least it would normally be assumed to be the motor's output power, not the input power. So definitely you could run more than 500 watts going into this motor. And what I'm going to do now is just ride around a bit in pass assist rather than throttle, just to see how they've implemented the basic pass control with the stock RadPower system, and see if it's sort of a fixed wattage for each assist level or if it's more or less a top speed. So right now I'm just going to ride around in pass assist mode 1, rather awkward bike to pedal. So we're doing 80 watts. As I pedal harder and we pick up speed, we're still at 80 watts. So it doesn't seem like the power is changing very much as my speed increases. Okay, so here we are in assist 2. I'm seeing 200 watts off the line at 10 kilometers an hour. Picking up speed, it's still around 200 watts. All right, we'll stop here and go to assist level 3. Here we are in assist level 3. So it's 340 watts. We're picking up speed and we're staying at 340 watts. Yeah, assist level 4, here we go. And not surprisingly, it's just running the same 500, a little over 500 watts that we had with throttle mode. And now that our speed's up, we see the power go down. And speed goes down, the power goes up. Oof. So that test ride showed us is that the stock motor controller really limits the input power to the motor to an even 500 watts. You get that full 500 watts when you run throttle only under any of the assist levels. And then when you're in the 4 different assist modes, each one is just running constant power, like 100 watts, 220 watts, 330 watts, or the full 500 watts. And that power doesn't change as your speed increases or decreases until you hit the speed limit, which seems to be set pretty firmly at 32 kilometers an hour. So the motor on this bike is a Bafang fat bike motor. Bafang makes these with a few different thicknesses of motor stator. Nominally, Bafang call them 250, 350, 500, and 750 watt versions. I'm not entirely sure which stator width is in this RadPower bike, but even their nominally lower power ones have no problem dealing with input power levels higher than 500 watts. So we can easily run this motor at a higher torque safely. Now, whether the speed can naturally go faster than 32 kilometers an hour really depends if that speed limit was based on the battery voltage in the winding RPM per volts, or if that speed limit was being, again, hard-coded within the motor controller itself. So we won't know, as it is right now, I'm not really sure which is the case, but when we hook up with our Grin Frankenrunner motor controller, we'll then have a very clear idea of how fast the motor goes without any electronic speed limiting. If it's naturally limited to 32 kilometers an hour based only on the battery voltage, voltage, then one could potentially upgrade to a slightly higher battery voltage. Instead of 48 volts, you could run 52 volts, or we could take advantage of the field weakening feature in the field-oriented motor controllers and then effectively run the motor at a faster RPM without having to swap out the battery pack. Our choice for this particular retrofit is going to be the RadRunner, and that's the highest power, highest phase current controller that we have right now. And because the controller, the bike, already has a platform for mounting the motor controller externally, there's no real downside to having this extra controller mount. It's smaller than the stock controller and will fit neatly inside that space. Now, where things get a bit trickier is determining all of the connector plugs that you're going to have to make in order to re-terminate the hardware that's on your factory bike with the connectors that are on the third-party controller or the Grin controller. Now, in this case, the battery power is quite straightforward. Our RadRunner uses the XT60 DC power jack, and because the battery is mounted external from the controller, all we have to do is re-terminate the wire that comes out of this battery cradle with an XT60 plug, re-terminate this with an XT60 instead of the overmolded connector, and that will just plug into the back of this. The trickier connector in many cases is going to be the plug interface between the motor controller and the motor. Now, lots of small power hub motors use the small 9-pin Z910 connector. This is an extremely well-standardized plug for lower power motors, and if you happen to have an e-bike system with that connector, that's ideal. We have a Basener Z9 motor controller that will just be plug and play with that existing connector. Now, Rad Power seems to have very consistently standardized on a larger connector standard, which is the Z916. This is a connector from Gillette that sort of has an octagonal shape on the inside. This is not a connector that Grin natively makes into any of our motor controllers, but we do now produce an adapter from the L10 plug to the Z916. And this will allow us to have a plug-and-play connection from our motor controller to the motor. But if your motor has a different style of connector for which there isn't an off-the-shelf adapter, then you're going to have to be prepared to cut the connector, cut the wiring right here, and solder on new leads to make a connector that matches what's on the motor controller. Here we're lucky we don't have to do that. Now, at the front end of things, there's a bunch of HIGO connectors on the handlebar linking up the brake cutoffs, linking up the throttle, all to a main cable harness. If we want to use the existing throttle and existing brake levers that are on here, we're going to, again, need to re-terminate these overmolded plugs with the JST connectors that are on the input of our cycle analyst. That's a fairly straightforward job if you have the right crimping tool. Another approach is simply to replace the throttle and brake levers with ones that already have the right connector on it. So depending on your comfort zone on re-terminating connectors, you may just prefer to buy matching plugs. The same goes with the pedal sensor. So on this bike, there is a pedal sensor on the left side of the crankset, and that pedal sensor has a HIGO plug to go into this motor controller. We really recommend, especially if you want a pedal or a torque sensor, to simply get a pedal or torque sensor from Grin that supports the cycle analyst connection interface. That's because we power the pedal and torque sensors with 10 volts, whereas most of these basic path sensors are only meant to be run off a 5-volt bus and will get damaged if you rewire them to be natively driven from the cycle analyst.
By the time this is off, I'll need to change the battery.
Going this bit. So this bike has through-frame electrical wiring, which is really clean when it's all installed. It's a kind of a pain in the ass to service or deal with, but luckily the openings are pretty big, and so we should be able to feed the whole main harness back through here, completely remove the existing controller and the initial wiring, and leave that channel open for us for the replacement hardware. So I think this is power to a rear bike light. So we'll pull that out. This looks like a programming port for configuring settings. And all we have left is motor power. So if we look at this controller, it has a maximum current of 11.5 amps. So with a 48-volt nominal battery, that of course gives us that 500-watt continuous power, which is all that we saw at the max power output. The replacement RadRunner fits just like a dream under the existing mounting plate. We don't even need to use any special attachment hardware, just 2 holes drilled in this plate will line up with the 2 holes in the RadRunner. This can go right back here, Super clean setup. We're going to wrap up for tonight, but finish this Frankenrunner installation tomorrow when we're fresh with new energy. And then we'll go through the tuning process of matching the motor controller to the motor characteristics, and then rerun our test around the blocks where we run this motor at substantially higher power and speed capabilities. So actually, you know what? So this has the cables pointing forward. Let me just see if that makes the right path length. So the motor connector's over here. Awesome. Yeah. So for the battery, we need to go to XT60 on this face, and the cable coming out of the cradle right now, if I fish it up through here, it's really not quite long enough to bend over and have enough slack to not put too much strain on that connection. So what we're going to do is just remove the cradle completely from the bike, desolder this wire from where it connects with the connector pins, and then solder the XT60 cable that came inside the Frankenrunner package directly to the base runner. If this cable was a bit longer, then we could have just left this all in place, snipped off the overmolded plug, and then soldered the XT60s in place here. It doesn't really matter one way or the other, but given the length situation, we're going to just switch it over from inside. Great. So now, yeah, we're going to want to solder on this cable to be just a little bit longer than what that was based on my sizing up. Here, they've covered the solder joint to the pins with silicone. Rather than soldering to the pin directly, I'm just going to make the solder junction to the wire that's there. So, yeah, hole's a little bit small, so let's just drill that out to be a bit bigger to fit this slightly larger cable. I'm going to put some heat shrink on each of these. That was a nice one. Picture perfect solder. Beauteous. So now we'll screw this back on the bike. It is a perfect fit. Look at that. All right. Now notice how the arrows don't actually line up. Perfect. Welcome to the world of e-bike plug standards. A simple back and forth loop at the front keeps things nice and tight. A couple zip ties there will hold it snug to the frame. So now we have the joy of fishing the cable through the frame tubing. And we'll see if we wish we had a snake for this.
Okay.
This would actually be much easier with the bike.
The other way around?
Yeah, like. Okay, so now I'm just fishing the brake cable perfect, and now we can use this to pull the psychoanalyst plug through here. So we'll just tape those together. Okay. Woo!
And a baby is born.
Oh, okay. I hate through frame cable routing. Somebody better appreciate this. The arrows will line up. Boomba, psychoanalyst. Yeah, that is great, actually. That's all we need to do down here. Great.
Cool.
All right, and here comes our first little moment of truth. Power, and we have power. So here we've got the motor controller hooked up and powering the motor, but it's not going to run until we actually set up the parameters inside the RadRunner motor controller to match the characteristics of this particular hub motor. So we're going to go through that process right now with our RadRunner software suite. It absolutely requires that you have a computer connection to the motor controller. These controllers are not plug and play with any random motor. We can pre-ship them with settings for the motors that we sell, but when you're doing a retrofit on a third-party bike, we really have no idea what the details are. Now in this particular case, it is a Bafang fat bike motor. We know that it's the G60 model, so I actually do know what the initial starting point parameters are, but we're going to show you how you would figure that out if you didn't have this kind of knowledge as well. So first thing is to plug this into the communication port. So super, it says RadRunner L10 connected. We've established communication with the motor controller, and now we're going to go through the tuning process. Now in this case, I'm going to pretend we know absolutely nothing about this hub motor, which is often going to be the case when you do a retrofit on a factory bike. They often obfuscate the markings or the model numbers, and there's just so many motor models out there that it's quite often impossible to find out the details of which particular motor drive is on an e-bike. So the RadRunner software suite has the ability to run an auto-tune routine, which can auto-detect most of the critical parameters. But there's one important feeding number that the system has absolutely no way to know. And that's what we have here, the number of pole pairs. And this here is effectively the number of electrical cycles that the motor controller has to drive the three-phase AC current to achieve one full rotation of the motor. So in a direct drive motor, it ends up being simply the number of pole pairs in the motor. So if you take apart a direct drive motor and you see 46 magnets, well, that's 23 magnet pairs. So there's 23 electrical rotations for each time the wheel does one revolution. In a geared motor, it's a bit more complicated. Not only do you have the magnetic pole pairs for the motor rotation, but then that motor is further geared down to the wheel rotation. So you're taking the number of pole pairs times the gear ratio. And often that ends up being anywhere from 35 to, in some cases, over 100 or 150 electrical cycles per wheel rotation. And the motor controller needs this information to correlate wheel RPM with the actual electrical frequency that it's driving things. So as this controller came out of the box, it was configured with 80 pole pairs, which is consistent with the GMAC motor, which looking at these parameters seems that it was set up for. And we don't know right now if that's correct, too high or too low. Fortunately, there's an easy way to determine what this number is without actually opening up and inspecting the motor or looking at the details online if you're able to find them. And that's through the dashboard tab. So the dashboard of our RadRunner suite shows the state of each of the hall signals. So as long as you have a motor that has a sensor connection with hall sensors, we can actually see what's going on each of the halls. So if you look now, the blue hall is illuminated. If I rotate the wheel backwards a little bit, you see that it turns off, and then it turns on again, and then it turns off again. Now it's important to rotate the wheel slowly. If you spin it fast, it'll do a whole bunch of cycles and you won't actually be able to see them. But if we're patient, we can just very slowly rotate the wheel one full revolution and count how many times one of these hall signals toggles up and down. So let's do that. I'm going to align the motor with the stem right on the bottom. So here that's just sitting right at the point of contact with the ground. And we're going to now slowly turn this wheel while we count the hall pulses. Now I mentioned that we rotate the wheel backwards. With a direct drive motor, of course, it doesn't matter, but on a geared motor, if you spin the motor forwards, so if you spin the wheel forwards, you're not actually turning the motor, so the halls won't change. So you can see that if I spin it this way, the halls on the screen stay not toggling. Once I rotate it backwards, we see them changing state. So let's align that stem back at the bottom. Great. And so here we go. So the blue hall's on, off. So that's now 1. Off. 2. Off. 3. Off. 4. Off. 5. Off. 6. Off. 7. Off. 8. This is riveting, eh? Off.
I'm amazed.
9. Off. 10. So at 10, you can see we're not quite at a quarter rotation. So to me, this is looking like it's probably going to be somewhere around 50-ish, 48, 50 pole pairs. So we can patiently keep counting, or we can do guesstimates. Let's just keep counting. 11, 12, 49, off. It looks like we're right at 50. Now that we have this information, we're going to put in 50 pole pairs. There's another variable that's not as important, but we still need to guesstimate the RPM per volt. It's basically a safe bet that any hub motor on a factory e-bike is somewhere around 8 RPM per volt, so not knowing any better, I'd usually just put that as a starting value. And now we can simply click Auto Tune. So here again, it was asking us correct number of pole pairs. We counted 50, and we're just going to guess 8 RPM per volt as the motor's kV constant, and hit static test. So the static test here is, you'll hear the motor buzz 3 times. So the static test was determining the resistance and the inductance of the motor phase winding. So it's reporting here 51 milliohms and 12 microhenries. That's great. And next we're launching the spinning motor test. Now the spinning test is going to actually power up and run the motor, and it's a spinning test that determines the actual RPM per volt, and it determines the Hall pinout in the Hall mappings. So in this case, we paid no attention to which Hall signal on the controller was connected to which Hall signal on the motor, because the base runner, phase runner, Frankenrunner motor controllers, they can all auto map whatever the Hall pattern is. What we have to be careful of is that the spinning auto tune rotates the motor. So you want to make sure that the wheel can spin freely, both forwards and reverse. And when I say spin freely in reverse, that's important because it means that the pedals are going to spin. So if it happens to spin the motor backwards, you want to make sure nothing's going to tangle in the pedals and get snared. And as you can see, my communication cable would indeed have gotten completely snagged if the motor was to spin backwards during this auto tune. So I'll tuck it out of the way there. And so here we go. So what we should see is the motor start to jerk a bit and then spin up. Make sure that we're not launch spinning motor test. Look at that. Okay, perfect. So the test completed, and it showed that the motor was 7.2 RPM per volt, and it gave a valid Hall pattern, so it's running in a Hall-censored mode, and it's running the familiar Bafang standard Hall pattern, which is not unexpected given that this is a Bafang motor with yellow, yellow, green, green, and blue, blue pinouts mapped. And that's it. So at this point, I should have no problem hitting the throttle and seeing the motor run. And if you ran into issues during that auto tune, there are other parameters specifically related to the current regulator and the PLL bandwidth that can affect the ability of the motor to even start running sensorless. If you're getting errors or faults when it's doing the spinning auto tune, it's sometimes useful to load default parameter files from existing hub motors that more closely match the motor that you're dealing with. We do have a number of motors already pre-mapped in our software available as defaults. Generally every motor that we sell here at Grin, and in this particular case, it is a Bafang G60 motor that's on this Rad Power bike, and you can see we actually have a Bafang G60 default. So rather than having initially counted the number of pole pairs and such, had we known in advance that was a G60 motor, I could have just selected it from here, hit apply. You'll notice that auto-populated us with 50 pole pairs, but it set a different RPM per volt, 9.3, and a different resistance and winding inductance. And that's because even the same motor model from the manufacturer can be available with different windings. So they spin at different speeds for a given voltage. So even if you select a motor that matches your model, you still want to run the auto tune in order to get the actual resistance and inductance and the actual kV value in order for the motor controller to perform without faults and issues. So now we have the basic motor parameters set that allow the controller controller to run the motor, but there's a number of other settings available in the software suite that will further determine the exact performance of this system. So you can see that when we loaded the G60 default parameter file, it set us with a 1,000-watt maximum power limit, a maximum phase current of 50 amps, and a maximum battery current limit of 20 amps. So these settings are going to allow, rather than the 520 watts limit that the previous motor controller did, they're going to allow upwards of, in this case, 960 to 1,000 watts, depending on the battery voltage, of power flowing into the motor. That's double the power. Now, you might think that that's reckless. We risk burning out a motor by running it at twice the power than the stock controller. In some cases, that would be. In other cases, it wouldn't. Now, this particular motor, we know can do 1,000 watts at modest bicycling speeds, no problem. It's quite a large motor stator inside, and the setting of 500 watts was really unnecessarily conservative. That's not always going to be the case with any factory bike, and of course, when you change these settings and put higher power into the system, you do put yourself at more risk of having failures, and of course, the onus is on you to not exploit that. The other thing is that our motor controller, this Frankenrunner, it's able to do over 90 amps of phase current. So if we wanted more torque off the line, we could boost this phase current to say 60, 70, 80 amps, not 6,000, 80 amps, of course, and correspondingly increase the torque output of the motor. But it's this phase current that really is the most damaging thing as far as risking overheating the motor, or in some cases melting the wires going into the motor. I'm not sure exactly what gauge wire was coming out of that cable harness, but judging from the diameter of the cable shroud, I wouldn't be too comfortable with 80 amps of continuous current through what looked to be about a 2 millimeter squared copper wire. But 50 amps is probably a bit lower than what it could take. So 50 amps is fine even for the small Z910 connectors. So I'm maybe just going to go 65 amps based on my gut experience here. And I'm going to leave the motor power. So this is a 14 amp hour battery pack. It should have no problem delivering 20 amps, even though the original controller only drew 11 amps. But if you push this limit too high, so say I set that to do 30 amps of battery current, of course, I'm going to need to have a higher maximum power here. There's a chance that at 30 amps, that would trip the battery management circuit. That would trip the BMS circuit of the battery, and the battery would just shut off once you try to drew full power, or it might, in some cases, blow the fuse. This battery, actually, when I had it off, I saw that it had a built-in fuse. I didn't actually pull it out to see. I suspect it probably has a 20 amp fuse in there, and so I think we should just leave that at 20 amps for now. If you find that blows the fuse, well then we'll have to further reduce that or replace it with a higher current fuse. So let's go back to, now leave that, yeah, 20 amps is, this 20 amp limit will give us really no more than 1,000 watts of power anyway. So now we have, so now we want to see how fast the system goes with the motor controller based just on the battery voltage and the winding kV. So this is a 20-inch rim, but with a big fat tire. We measured it to be about 22.1 inches in diameter. So I set the wheel diameter to 22.1, hit save parameters, and now if I go over to the dashboard and hit the throttle, we'll be able to see how fast that results in a bike speed. So spin up the throttle, and you see unloaded, it's doing 34 kilometers an hour, 33 kilometers an hour. Motor's spinning at 320-ish RPM. So what this means is that the limitation that we saw when we were riding previously with the stock motor controller, where the power started cutting off just as we were approaching, or just as we were exceeding 30 kilometers an hour, that was most likely not a hard speed limit in the motor controller, but simply the fact that this RPM per volt motor with a 48 volt battery and this size wheel isn't going to propel you really over 30 kilometers an hour. The unloaded speed is 34. Once you put any drag on the motor, then the bike speed is going to drop down to that 30 to 32 kilometers an hour that we saw it topping out at. So with the Frankenrunner motor controller, we have the ability to override this limitation to some degree, and we can do that with field weakening. So field weakening is we call it top speed overdrive in the bottom right pane of the basic setup tab. So this allows us to effectively play with the timing of the three-phase current going into the motor to kind of cheat that maximum RPM limitation. But it comes with a small hit on efficiency. So the more field weakening current we allow, the higher we'll be able to boost that top speed. But while we're running with that field weakening current at those higher speeds, the motor is definitely less efficient than if we just had a higher voltage battery or faster winding. But let's just say we wanted to cruise more at like 36 kilometers an hour rather than 30. I can change that to 5 amps. And we'll go to the dashboard and see what 5 amps does to our top speed. So now you see the unloaded speeds increase to 36 kilometers an hour. So that's an improvement, but if we want to go 36 while we're loaded, we need the unloaded speed to be even higher still. So I'm going to just see what going to 10 amps of field weakening does. So 10 amps, save parameters, dashboard. Awesome. So that gives us basically 40 kilometers an hour of unloaded speed, so that should have no problem now doing 36, 37, riding on the straight stretches on the ground, and for a lot of people that's going to be a nicer kind of commuting velocity. So I think these settings are going to be pretty fun and appropriate for the motor. So now we need to do some setup on the cycle analyst. And the cycle analyst is a main dashboard, but it's not in any way communicating with the motor controller. So the details that you see here, we were seeing the motor speed on the dashboard. That's the speed that the controller determines based on how fast it knows the motor's spinning and the number of pole pairs. The cycle analyst isn't privy to that information. So the cycle analyst speed display is dependent on there being a wheel speed sensor inside this hub. Now, we took a bit of a gamble. The stock display that's on this handlebar doesn't have any speed readout. So it's quite possible that in the interest of economy and price savings, this Bafang motor was ordered without any internal speed sensor because the bike platform on which it's built doesn't have a speed display readout, so there'd be no reason to necessarily include it. But more often than not, most of the geared motor e-bikes sold in the last 5 years do have an internal speed sensor. Most of the time there's 6 magnets inside the hub shell, so we get 6 pulses each time the wheel rotates, but sometimes there's fewer than that, and in many cases there's just 1 magnet. So luckily we can use the cycle analyst to easily determine how many speed pulses, if any, there are in the inside the motor shell. If the very first menu item here, Setup Speedometer, has the number of pulses per rotation configured, here you can see it's set for 23. That's the default for a lot of direct drive motors. It's definitely going to need to be changed for this one. But right beside that, you see the P with the little arrow pointing up. That's the state of the digital pulse signal that's used as a speed indicator. Now, as I rotate the wheel, what we want to see is how many times does that P arrow switch direction. So instead of pointing up, switch to pointing down. And each time it does, that means that there's a magnet passing a sensor inside the motor shell. So far I've been rotating the motor and it hasn't pulsed down once. I'm really hoping that it does at least 1 pulse, because if it doesn't, then we have no way to see the speed based on the internal connection to the motor, and we'll have to add an external speedometer sensor, which is doable, but just a step I was hoping we could avoid. So as I turn this motor around, does that arrow talk? Yes! Woo! Saw that? So now it went down and then up. So right here is where the magnet inside the motor shell is passing a sensor, but that happened only after a full rotation of the wheel. I spin it again, and I have to do another full turn before it pulses down, as you just saw there. So this means this is set up with just 1 speed pulse per rotation. That's enough to get a speed reading for sure, but when you just have 1 pulse per wheel rotation, it means that the cycle analyst is not going to be as fast at showing your speed when you take off, and it's going to be slower to update your speed as you accelerate and decelerate. So there's just a little bit more lag, and it's also not as accurate as a speed control loop. So if you want to set the cycle analyst to limit you to say 10 or 15 kilometers an hour, it'll do a better job with a higher speed pulse. So let's set the wheel circumference. So again, as we showed the other day, this needs to be set to 1765 to match a 21.1 inch diameter. And as we just determined, this was not a 23 pole, it wasn't even 6 pole as I was hoping. It's just a single pole wheel speed sensor inside the hub. And that's that. So now we see we have 1 pulse and 22.1 inch diameter. So now when I hit the throttle, I should see speed on the cycle analyst, and I do. And you see it shows exactly the same 40 kilometers an hour that we were able to see on the Frankenrunner suite, on the Phase Runner suite. So now all that's left to make this a usable upgrade is properly mounting the throttle to the handlebar, getting rid of some of the extraneous components that are left over from the stock electronic drive, and we should be good to take it for a spin around the block and just see how the system compares to what we had before. So now we're going to do that same test ride with the replacement motor controller running with the higher battery current capability as well as the 10 amps of field weakening current, and do the same kind of thing looking at our power versus speed curve and just get a feel for how the ride compares. All right, so as you saw in that last run, even as we approached 38, 39 kilometers an hour, we still had 900 watts of power going into the motor, and we hadn't yet reached the speed where the motor power was cutting off. So we're going to try one last chance on this straightaway to see if we can actually accelerate past the point where we see the motor power drop off. But as you can see, that 10 amps of field weakening had a huge effect in boosting the ability of the motor to produce power above that 32 kilometer an hour speed where it was previously maxing out. So now we should see where that point is. Let's go. Okay, 35, 38, we're at 40 and 900 watts, 42, 800 watts, 44, 700, woo. Damn, that's 44 kilometers an hour. So even with the 47 volt battery like we had yesterday, you can still see we clearly have been able to sustain 40 kilometers an hour. Those speed bumps are no fun at 45. And the cap of this started to fall off.